can talk about this more later on. And if you take the special case with I equals j, you get this, it's really nice. I mean, you've got the sum of these powers of q and these quotients of these different guys, product of these guys, and it always collapses down to 1. But what's interesting is these are finite sums. Okay? They're not like infinite q series, okay, but they're finite quantities. So
but that's probably well known.
I don't know. I haven't found it anywhere. So
no, I think it's specification of one of the big ones.
Okay.
Look in Fine's.
How you got it?
You think
Fine's book?
Fine's book?
Yeah.
Okay.
No, I can give you the reference.
Okay.
It's beautiful. By the way, they act. Now, once you get it, I think it's a special case of one of the biggest.
Okay.
And also could be proved with the Q-Zalberger.
Okay. Yeah, prove it with Q-Zalberger, that's right. And then here's one more. Here I've got these BST. I'm filling a matrix with these guys, and these are polynomials, finite polynomials, which do not have a nice closed form expression. And you do your LU decomposition, it looks nice what comes out, and you end up getting this scary looking formula come out. But my point is I'm using an unconventional use of LU decomposition to motivate all these different looking formulas. All right, something different for the number theorists in the crowd. Here's an old result which hasn't gotten a lot of attention as far as I know, Gauss's cyclotomic formula. So P is an odd prime. P prime will be P times possibly minus 1. And the claim is if you build this expression, this has to be a polynomial because P is odd, so the x plus y will divide into there. You can always write this as the square of a polynomial with integer coefficients minus the same kind of thing times the P prime. Now, how could you motivate something like this experimentally? You can do a factorization over a field extension. Maple has this built in. So if you enter this quantity and you factor it, and with that square root of 5, you'll have these two different terms pop out. And you can see with the difference of squares, I can write it like this, and this has the form which is claimed up here. So this is Gauss's cyclotomic formula, a special case. And so I worked with Bud Brown, who's at Virginia Tech, and we came up with the generalization. Oh, I see an error I have in my slide, but you probably know what a circular matrix is. I start with x1 to xp. I shift everything over by 1, shift the next row over by 1, till you get down to the bottom, and you'll see if you do one more, it brings you back up to the top row. So I mislabeled these indices here, sorry. So I'm going to start with this circular matrix, and we claim we have something just like in the last slide. The determinant of the circular matrix divided by that sum has the same kind of form. And this was all motivated by the same thing. I did a factorization with the appropriate field in Maple. I saw something happening there, and then Bud was able to use some techniques from Galois theory and so on to come up with the proof. All right, something different, another number theory kind of thing. My colleague Carl Dilcher and I were interested in these kind of binomial sums. And the reason is because if this n is a prime that's 5 or larger, a prime greater than 3, we found that this a sub p was congruent to minus 1 mod p cubed. There's a result called Wolstenholme's theorem, which gives you something for central binomial coefficients. And so this does not have a closed form expression, but we thought it was interesting that it was showing this kind of behavior. So we conjectured it and then proved it. But we wanted to do some more experiments on terms of this form. And you can see calculating all these binomial coefficients would take a while. So we thought, is there a quick way of calculating these ANs? And so we used Zylberger's algorithm and got our 3-term recurrence relationship, and then we can generate these ANs very high, no problem. All right, something very different. This is with Victor Moll, who's at Tulane. So we are interested Victor, I call him Mr. Integral because he loves integrals, solving all things integral. So he was looking at this class of rational functions. I've got 4 parameters, A, B, C, D, E. And Victor was able to show that if you transform, replace A, B, C, D, E with A1 to E1, that the value of the integral does not change. So it leaves the integral invariant. Why this is nice is because if you then keep iterating those 5 values, you end up approaching values which make this integral easy to compute. So we wanted to try to understand which choices of A, B, C, D, E can you get this iterative dynamical system converging to something nice. And we noticed that what the new A and B depends only on A and B. So let's start with, instead of thinking of this 5-dimensional dynamical system, let's look at the subproblem, the 2-dimensional one. Notice that it involves this T term, but T depends only on A and B itself. So we want to know what happens if you start with some A-B pair, what it transforms to, and where the set of points generated by this wander in the plane. You have to be careful which point you start with, because if you don't choose the right point, you're going to dance around all over the place, and it's not settling down. It ends up that this curve, which seems to be produced as a border to these points, that's a very important curve. It corresponds to when the discriminant is equal to 0. So this expression equals 0. And using the idea that this curve is invariant under the dynamics suggested that we use Maple to help us expand this all out and factor it. And we saw we got this nice identity come out. And this identity was key in proving that if you start any starting point above this curve, that you will converge to the point 3,3. 3,3 is a very lovely point for this process because you see what happens if you plug 3,3 in here. Your bottom factors very nicely, and everybody smiles, and you can go home. But Maple, the experimental side, was helpful in coming up with this identity here. All right, let's look at a very simple map, a 2-dimensional map. So xy is mapping to this new pair. If you had a linear map, you can solve it exactly, there's no problem. So this is about as simple as you get. It's a quadratic nonlinearity. This has some interesting properties. First of all, clearly 0, 0 is a fixed point, and using standard stuff, looking at the Jacobian of the transformation, you show that 0, 0 is locally attracting. More importantly, the basin of attraction, that's the set of points which will get pulled into 0, 0, is symmetric, and that's not hard to see because you've got these 2 squared quantities coming up here. And moreover, one can build the so-called energy function or Lyapunov function to show that if you start in the interior of the square, you will get pulled into 0, 0. Moreover, you have a 3 cycle. If you start at 0, 1, it maps to this, and back to 0, 1 again. So some of you might remember there's a famous paper from 1975, period 3 implies chaos. So whenever you see period 3, your chaos antenna should come up. Okay? So it tells you there's going to be some complicated dynamics underlying this process. So this is a picture of a piece of the basin of attraction in the first quadrant. We have symmetry in all 4 quadrants. And I know this didn't come out terribly well on the slide, but this is all supposed to be solid. Remember I said the interior of the unit square. So there's that piece of the interior of the unit square. But you've got these branches going out here, and all of this stuff, this is not just numerical noise. These are pieces. You've got all this fine strands and stuff that comes up in the basin of attraction. And in fact, you have something scarier because of that 3 cycle I pointed out too. If this, I've got some scaling going on, this is supposed to be the square. But I've got the blue curve here, a green curve and a red curve, and each of these curves maps to one of the other ones, and you've got a 3 cycle with the 3 different curves. But notice this blue one, here I'm starting at one of the points, which is part of the 3 cycle. I numerically build the unstable manifold coming out of that point, so it goes up, comes around, comes over here, down, up, and something, I'll say verboten, okay, it's kind of almost illegal. I have this manifold crossing itself. In continuous dynamics, this is impossible, it doesn't happen. But in discrete dynamics, it would be allowed. But this is also your telltale sign. If you've got a manifold crossing, invariant manifold crossing itself, and you know you've got dynamical trouble, you've got chaotic behavior going on. So Maple was able to help me see this behavior, do the plotting, build the manifolds, and so on. All right, one more thing. I want to look at apiary limits. So many of you will know that apiary showed that zeta of 3 is irrational. That was in the late 70s. And a part of apiary's proof that helped him to do it was to look at these expressions. And so this is long before Zeilberger's algorithm came out. So he proved by hand this 3-term recurrence relationship for the A's. And then he looked at a corresponding sequence which satisfied the same difference equation, we'll call it B sub n, where I have my 2 initial conditions are B0 equals 0 and B1 equals 6. So this generates a unique sequence via this difference equation. And if you take the ratio of these terms, it approaches zeta 3 over 6. This was something that apiary showed in his proof. And using knowledge from the theory of difference equations, you can actually transform this limit into an infinite sum involving only the A terms. So I don't really need this auxiliary B sequence, so to speak. I can define the A's like this, and I have this expression. And this is, from a numerical perspective, a much nicer way to compute zeta of 3. There are faster series than this, but this is nice because you can see these A's are going to be growing pretty quickly, and so this has a geometric growth as opposed to the definition from the Riemann zeta function. Okay, well, this is a nice result. So I wanted to explore things of this spirit. So I said, let's take these terms. And in the 80s, somebody was able to prove that this sequence, these C sub n's, satisfies this 3-term recurrence relationship. Now, of course, Maple does it in a second. But I wanted to mimic what we did on the last slide and see what comes out. And so using the theory of difference equations, it suggests that I want to look at this kind of series. On the last slide, I had a k plus 1 cubed and ak plus 1, and just a 1 on top. The theory of difference equations, because of this minus 8 here and some other stuff, suggests I should look at this, and this might be a nice number. Just like on the last slide, I had zeta 3 over 6 as my nice number. So this has geometric convergence, so I compute a whole bunch of these added up. Maple has a nice command, if you don't know it, called identify, which is a souped up version of the PSLQ algorithm. And identify, you give it a number, and it will make an intelligent guess as if this has a nice form. And identify tells me it's pi squared over 24. And I have no idea how to prove this. Maybe for Doron it's a proof already. Okay, but I have no idea how to prove it.
No, I think it's known in Van der Putten's paper.
Right.
He mentioned that if you use this, you get another sequence approximating zeta 3, zeta 2, zeta 2.
Well, I know this is a scaled version of zeta 2, but this is a different kind of.
Yeah, but I think in the footnote in Van der Putten they mentioned it. It's not explicit. I think at least they knew about this. But the analogous proof doesn't go. The irrationality measure is not good enough to prove irrationality.
So I think in that paper, instead of having the squares, they drop the squares and they look at that, and that's the result.
That's not 2, but if you drop one of the squares, it's zeta 2.
But here I'm looking at different series.
Yeah, but look at one of the footnotes mentioned exactly this sum
Okay.
as a possible analog of proving that Z of 2 is rational. Although it only
Okay, I thought that footnote was only for that one specific series I had on the last slide, dropping the squares. Okay, well, let me finish up here, 'cause I'm almost done. So the suggestion is this is pi squared over 24, and I can build a whole bunch of other formulas like this type. You start with something like this, you get this guy come out using Zioberger, then you use your theory of difference equations to build a candidate sum you think will be nice, turn on your numerical recognition stuff and see what comes out. And lastly, I want to show an example with polynomials, not just numbers. So again, I apply Zioberger's algorithm to this. I get this 3-term recurrence relationship, use the theory of difference equations, and it suggests that I look at this kind of expression. Now now I don't have just numbers. Now I have all these expressions here with these x's. And what am I supposed to do with all of this? Now you could say, well, what if I took the special case x equals 0? You don't want to do that. Because if you do x equals 0, these are all equal to 1, and you put 1s in here and you have the harmonic series. That's bad. So what am I going to do with this? I expand it around x equals infinity in Maple, and look what comes out. You can see a pattern from there. I don't even need Sloan to see that pattern. Okay? And so there is my conjecture associated with this starting series. So lots of interesting stuff you can come out. I know I'm preaching to the choir, but I'm glad you let me share a bunch of my different work. Thanks for your attention.